Praveen ma'am, we are live now. We can start the session.
Okay, sir. Okay, sir. Good evening, all of you, and a very warm welcome to all of you to the 2-week refresher course in applicable mathematics. Today also, we are honored to have Professor S. Arumugam among us. So without taking much time, I would like to request Sir to enlighten us more about graph theory.
You have to enable me for sharing. Says host disabled for screen sharing. So you have to change in the system and allow me to screen share.
Sir, are you able to share your screen or not?
It says the host has disabled you from screen sharing.
Okay, okay, sir.
So you have to.
Rajesh sir, please allow sir to share his screen.
Okay, now it's okay.
It's okay, sir. Okay, sir. Okay.
Is it visible? Screen
Yes,
is
sir.
visible?
Yes, sir. The screen is visible.
Okay. So we shall continue with our discussion of cellular manufacturing system. I am happy to welcome all the participants for the second talk on the topic. Today being the National Mathematics Day in particular, the birthday of Srinivasa Ramanujan. So particularly happy that my lecture falls on this date. Okay. Let me just quickly recall what is cellular manufacturing as we discussed yesterday. So the input for the problem is a set of machines and a set of parts and a matrix whose ijth entry is 1 if the part Pj requires the machine Mi for processing. Okay. Now the problem is to divide the large manufacturing system into small cells where each cell is a well-defined unit of the whole system. Okay. Fine. So this is what we want to do. So as I pointed out yesterday, we have converted the problem to a graph theory problem where the input is converted to a bipartite graph with parts becoming one part, machines becoming one part, and a part joined to a machine if the corresponding entry in the matrix is 1. So for this matrix, we have this graph. Okay. The problem is to split this graph into cells such that intercellular movement is minimized. Okay. Fine. So this is closely related to the concept of edge connectivity in graph theory. What is edge connectivity? Minimum number of edges to be removed from the graph so that the resulting graph becomes disconnected. For us, disconnected means each component will become a cell. But in cellular manufacturing problem, we don't want a cell consisting of just one vertex. Okay, it's meaningless. Therefore, each cell must represent a non-trivial connected graph. Okay, each cell must represent a non-trivial connected graph. So what is the minimum number of edges required to get this? I call this as the restricted edge connectivity of the graph. So restricted edge connectivity is the minimum number of edges to be removed, so that after the removal, the graph splits into k non-trivial components. Very important, k non-trivial components. For example, in this example, I can't remove P1 M1, because if I remove P1 M1 becomes an isolated vertex. Okay, which I don't want. Which I don't want. So you see, the problem becomes different from the usual edge connectivity problem. So what is the minimum number of edges whose removal gives a disconnected graph in which every component is non-trivial? I call this restricted edge connectivity number of the graph, because you have put a restriction, namely every component must be non-trivial. Okay, we can go still further. Perhaps the problem has, say, 100 parts and 30 cells, 30 machines. Then how many cells you want for an efficient functioning of the whole system? So sometimes the number of cells may also be specified. In other words, given a bipartite graph and also a positive integer k, I want to find the minimum number of edges to be removed, so that after removal, we get exactly k non-trivial components. Okay. I fixed the number of components also. That is, the number of cells is fixed by the industry fellow. So I must accommodate such concept. So what is the minimum number of edges to be removed, such that after removal, the graph becomes disconnected with exactly k non-trivial components? This I call k restricted edge connectivity of the graph. Okay, k restricted edge connectivity. So new parameter from graph theory perspective, but important parameter from application perspective. So it's a strong applicable mathematics. Okay, this parameter is immediately applicable to a cellular manufacturing problem. We want exactly k cells. Okay, so it's a nice new graph theoretic parameter, k restricted edge connectivity of a graph. You can try to develop the theory of this parameter. I give you 100% guarantee it will get accepted in good journals, because we need this concept for application. Okay, so k restricted edge connectivity I denote by the symbol beta g comma k. Graph G and k is also specified. Beta g comma k is the minimum number of edges whose removal gives a disconnected graph with exactly k non-trivial components. Okay, fine. So I denote this parameter by the symbol beta g comma k. Determine beta g comma k for standard graphs. That's a good problem, good research problem. Okay, determine beta g comma k for standard graphs. Okay, fine. For example, if the graph itself is disconnected, beta g comma k is 0, as in this case. So that's a trivial case which we shall not consider. Okay. So now, what is beta gk? I have determined this parameter for cycles, trees, and complete bipartite graphs, and any complete graph, any bipartite graph, complete bipartite graph minus a perfect matching. Skn comma n minus a perfect matching. For this family of graphs, I have determined the value of the parameter. Okay. For example, for a cycle, for a complete bipartite graph, the answer is this number, k minus 1 into m plus n minus k. Okay. I want to split into exactly k components. How many edges are to be removed? The minimum is this number. For example, we take k3 comma 3, okay, complete bipartite graph with both sides having 3 vertices. You substitute, you'll get the answer. Okay. Fine. So for complete bipartite graph, the number is completely determined. Again, for cycle, it is very, very simple. Okay. For a cycle, it is very simple. For a tree also, it is very simple. So for a tree, beta g comma k is k minus 1. Okay. For a tree, the parameter is exactly k minus 1. Not only that, I have completely characterized all graphs for this is exactly equal to k minus 1. The complete characterization is beta gk is k minus 1 if and only if g can be obtained from a tree of order k and put at every vertex a non-trivial bipartite graph. Put at every vertex a non-trivial connected bipartite graph. Blow the tree. You draw the tree with vertices v1, v2, vk. At v1, attach a bipartite graph. At v2, attach another bipartite graph, and so on. At vk, attach another bipartite graph. You get large family because the choice of bipartite graph is completely in your hand. Okay. And this is the only graph for which beta gk equal to k minus 1. It's completely characterized. See, these papers got easily accepted because of the application. Again, for a tree, it's automatically k minus 1 because you don't need to attach any bipartite graph. You don't attach any bipartite graph, I get for any tree, beta gk is k minus 1. For a cycle, it's exactly k. For a cycle, it's exactly k. Can I quickly prove this? Take a cycle on 10 vertices. I want to delete edges to get exactly 3 non-trivial components. How will you proceed? 10 vertices lying on a cycle. Okay, you put a cycle. 10 vertices are there on the cycle. I want to remove some edges and get exactly 3 non-trivial components. How will you start deleting? I'm saying exactly 3 for 3 components. You first delete one edge. The cycle becomes a path. The cycle becomes a path. Now you already know that for a tree, it is k minus 1. Okay, for a tree, it is k minus 1. So for the path, it is k minus 1. You remove one more edges. Therefore, it is k. So trivially, I am getting the proof. Okay, trivially, I am getting the proof. In fact, for any unicyclic graph, this result is true. for any unicyclic graph, this result is true. Because remove one edge on the cycle, the graph becomes a tree. So for which the number is k minus 1. I have to remove one more edge on the cycle. So for any unicyclic graph, the result is true. I will put even here because I am completely restricted bipartite graph. The cellular manufacturing problem is only for bipartite graph. That's why I will put even cycle here. But the result is true even for odd cycles. Okay. For a complete bipartite graph Kn, n, you remove a perfect matching. For this graph also, I have exactly found the answer. Some formula. Okay, fine. So only this family of graphs I have found. The problem completely remains open. Okay, try to find bounds for beta gk. Okay, then I went for one more generalization, which is also coming in the application. Because in a large industry manufacturing system, they don't want to have small cells. If you have a small cell, work in that cell will not be much. So economically, it may not be viable. So they put a restriction that every cell must contain at least L vertices. Okay, every cell must contain L vertices. So what is the problem now? Given a bipartite graph, given K and L, both of them are given to you. Say bipartite graph is given, two integers K and L are given. What is the minimum number of edges to be removed so that you get a disconnected graph with exactly K components and such that every component has at least L vertices. Okay, I call this K, L restricted edge connectivity of the graph. K, L restricted edge connectivity. For a parameter to be meaningful, n must be greater than or equal to KL, because you want K components. Every component must have at least L vertices. So totally, you must have at least KL vertices. So n must be greater than or equal to K, greater than or equal to KL. Only then this parameter is defined. This parameter is completely unexplored. I introduced this concept in the PhD thesis of my student and put some preliminary results. So if you study this parameter, I denote it by a symbol beta G, K, L as a notation. Beta G, K, L. The minimum number of edges to be removed so that the graph becomes a disconnected graph with exactly K components, and each component has at least L vertices. What is the minimum number? It's a beautiful parameter in graph theory. It's a beautiful parameter in graph theory. You can write good research papers on this parameter, and no one will ask you what is the motivation for the parameter. Because you can immediately say the motivation, the necessity comes from cellular manufacturing problem, where a big manufacturing industry wants such a breaking of the graph. Okay. So try this parameter for various values of K and L. Beautiful research problem for a scholar. Okay. Develop the theory of KL restricted edge connectivity of a graph. Develop the theory of this parameter. Okay. Fine. Now let us try to come to an algorithm for solving the cellular manufacturing problem. Okay. Initially, I am going to break it into 2 cells. Afterwards, I can repeat and have more cells. Okay, my initial algorithm will split the graph into 2 cells. Okay, fine. So given the bipartite graph, I want to develop an algorithm to split the graph into exactly 2 non-trivial components. I'm initially taking the case k equal to 2. Afterwards, we shall extend it for other k. That's easy. Okay. Then, mechanical engineering people have developed some numbers called grouping efficiency, grouping efficacy, grouping measure, grouping index, cell efficiency to check how good the solution is. See, given a solution to the cellular manufacturing problem, how good the solution is from the application perspective. So for that, they developed certain measures which gives you an idea of how good the solution is. Okay, how good the solution is. For example, I'll give 1 or 2 examples. GRE. What is GRE? It was introduced by Chandrasekharan Rajagopalan. You take a cellular manufacturing problem, rearrange the machine component incidence matrix such that it becomes a block diagonal matrix. Okay, then any submatrix corresponding to a cell will be a block. Okay, so in this decomposition, they define GRE to be Qn1 plus 1 minus Qn2, where Q is a user-defined weighing factor, which is between 0 and 1. So you have got this parameter to develop or to decide how efficient the solution is. Similarly, they have defined efficacy. I won't go into the details of all these parameters. This will take so much time. The point is, certain measures have been developed by engineering community to study how efficient a solution is to the cellular manufacturing problem. Okay. If this number is good, then it is within a certain range, they will say it's a good solution. Like that. Okay. Fine. Good. This again something called grouping index. Okay. And grouping cell efficiency. How efficient a particular cell is. They have developed a number for this idea. Okay. I'll use this later. Now, the algorithm that I have developed for solving the cellular manufacturing problem uses a standard technique in graph theory called depth first search. Okay, depth first search. It is a systematic way of visiting all the vertices of the graph. Okay, a systematic way of visiting all the vertices of the graph. This is an algorithm called depth first search, DFS. What's the algorithm? You start from an arbitrary vertex V. That's the first vertex you are visiting. Okay, take an arbitrary vertex V, say that it has been visited. Then take an unvisited neighbor of D and mark it as visited. Is that clear? Start from an arbitrary vertex. Say it is visited. Go to an unvisited neighbor of that vertex. Mark it as visited. Then go to an unvisited neighbor of the second vertex. Mark it as visited. Then take the third vertex and go to the unvisited neighbor. Proceed like this. If you reach a point where all the neighbors have already been visited, you backtrack. Go back. Okay, backtrack. Use the same path for going back. If you travel from V1 to V2, V2 to V3, V3 to V7, V7 to V9, in backtracking, you must V9 to V7, like that. The same order you should preserve. Okay. So suppose you started with V1, you visited V3, you visited V7, you visited V9, you visited V11. Now all the neighbors of V11 have already been visited. Go back, retract, go to V9. If there's an unvisited neighbor, start from there and continue the algorithm. So keep moving until you reach a vertex which has an unvisited neighbor. And from that vertex, continue the visiting process. So you do this visiting process. Suppose all the vertices have been visited. Okay, all the vertices have been visited. Then what can you say about the graph? Every time you are visiting a vertex not yet visited. And you are continuing the process until there is no other vertex to be visited. So, if this algorithm terminates by visiting all the vertices, then we can conclude the graph is connected. So DFS gives an efficient algorithm to check whether a given graph is connected. Suppose you have finished one searching and still some vertices are remaining unvisited. That means what you got is one component. You go to a new vertex, start visiting, and that will give you a second component. So if the graph is disconnected, then the DFS algorithm will tell you the number of components. Not only that, each component it will tell you. Vertex set of each component also it will give you. So DFS is a powerful searching algorithm to visit all the vertices of a graph in a systematic way. The algorithm is very simple. Start from any arbitrary vertex and keep visiting unvisited neighbor of the current vertex. And if for the current vertex, all the neighbors have already been visited, backtrack until you reach a vertex which has an unvisited neighbor. And start continuing the algorithm at that vertex. Repeat this process. That's all. So this is what is called DFS, the first search algorithm. Now, simple question. In a DFS algorithm, look at the set of edges you are traveling during the search. So for V1, you are visiting V3. That means V1, V3 is traveling in the algorithm. From V3, you are going to V7. Then V3, V7 is used in the algorithm, and so on. So take the set of all edges used in the DFS. What can you say about this set of edges? What can you say about the subgraph induced by this set of edges? As you see, just going down, keep on going down. then backtrack, again keep on going down. Right? So is there a possibility that a cycle will be created among the edges of the edges of traveling? In a DFS algorithm, can you say that the set of all edges visited will never form a cycle? In other words, if the graph is connected, you will end with a spanning tree. And if the graph is disconnected, you will end with a spanning forest. So this is the idea. Okay, this is the idea. So I have a systematic way of visiting all the vertices of a graph in a specific order. Okay, I'll give an example. We'll take a big example. Let us take this example. This is a problem given in an engineering journal. This actually got 11 parts and 7 machines. And they are given the matrix. Okay. Fine. So I have this graph. 11 parts in one side, 7 machines on the other side, edges representing the fact that the part requires the corresponding machine for processing. Okay. I'm going to apply DFS. As I told you, you can start from any vertex. No problem. The result will be more or less the same. It has been proved by the computer science people that in a DFS, the starting vertex doesn't matter much. Okay. The starting vertex doesn't matter much. Okay. The result will not be affected in a big way. Okay. So start with M5. Okay. So start with M5. From M5, I visit P3 because M5 is joined to P3. P3 is the unvisited neighbor. So from M5, I visit P3. Afterwards, from P3, where I will visit? From P3, I am visiting M6. You look at from P3, I am visiting M6. Then it's there. From P3, M6. From M6, go to unvisited neighbor. P7. From P7, M7. From M7, I come to P8. Now you see that M7, M6, M5 has already been visited. We are at P8. So go to the figure. We are at P8. We are at P8. What are the neighbors of P8? M7, M5. Okay, M7 and M5. M7 and M5 has already been visited. So what I should do now? I backtrack. From P8, I backtrack to M7. Okay, so from P8, I backtrack to M7. So now this algorithm is clear. I backtrack to M7. Now look at M7. Is this unvisited neighbor? This unvisited neighbor. Okay, from M7, I have an unvisited neighbor, P11. Continue. So is the algorithm clear now? I start from an arbitrary vertex, keep visiting vertices of the graph. A neighbor is visited every time. A neighbor of the current vertex is visited at every time. And if for a particular vertex, all its neighbors have already been visited, like for example, P8 here, I backtrack and from there I start. Okay, from there I start. This is how the algorithm works. So DFS algorithm gives a spanning tree of the corresponding connected graph. You should throughout assume the graph is connected. Okay, so DFS algorithm gives you a spanning tree. Excellent. Now I am going to use this tree to get answer for the cellular manufacturing problem with exactly 2 steps. So this is how I am developing the algorithm. Okay. See, total number of vertices is, let's go back to the graph. Totally we have 11 plus 7, 18 vertices. I shall try to break this tree at some point so that it more or less becomes equal. More or less becomes equal, not exactly, more or less. Okay. Suppose I remove P11, M2, P11, M2. The graph becomes 2 components. One component has 7 vertices, the other component has 11 vertices. So I use this tree to split the graph into 2 components by removing one edge from the tree. So you see, my algorithm is very, very nice. Start from the bipartite graph, apply DFS, get the DFS tree, which is a spanning tree, and remove one comfortable edge from the spanning tree so that you get 2 non-trivial components. See, I will not remove M7P8, for example. That also will make the graph disconnected, but one component will be just a single point, which is not permitted. I want non-trivial components. Okay, so I have to remove an internal edge of the tree, not a pendant edge. Remove a suitable internal edge of the spanning tree. See, if you remove, for example, P1, P7, one component will have just 4 vertices. One component will have just 4 vertices. The remaining will have 14 vertices. Okay, like that. So I choose a comfortable edge that gives the splitting in a nice way. Okay. So that is what I am doing. I get a 2-cell partition of the graph G by removing one comfortable edge from the spanning tree of the graph, from the spanning tree obtained by the DFS algorithm. Having got such a partition, I just try to check whether some interchanging of the vertices will bring down the number of exceptional edges. This is a method of doing it. I try to check by some method whether the number of exceptional edges can be still brought down. Now you go back. I am removing P7, P11, M2. P11, M2. Look at the original graph. Remove P11, M2. This is how I am removing. But you see, this is not a disconnected graph. Okay? This is not a disconnected graph. So you must understand little carefully. Disconnected comes only from the tree. Okay. For example, I take P11 or let me see. I look at neighbors of P11. P11 has neighbors M7, M5, M2, okay, M7, M5, M2. Okay. Therefore, you see, P11, M7 is within the component. P11, M2 is within a component. But P11, M2 is not within the component. If I'm removing M2. P11, P2 is not within the component. Because my components are that side and this side. P1, P11, M2 I am removing. So what's the exceptional edge? P11, M3 is an exceptional edge. Because that edge is present in the graph, it goes from one component to another component. That means this part has to be carried to another cell for processing. That is the idea. So that set of edges I have to minimize. So I have developed some more techniques to bring down the number of exceptional edges by making some computations. I am removing something. I am not going into the details of this computation. Okay. I am actually taking two vertices from different components and look at the subgraph induced by putting back one of the vertices, and then look at the number of exceptional edges for this new rearrangement, and it comes down to be this number. So if A2 is bigger than A1 and B2 is bigger than B1, then you see beta G pi becomes smaller than beta G pi 1. So number of exceptional edges get improved by some process. This process also I do in the algorithm. Okay, good. Such a thing is called interchange of two vertices. I interchange the two vertices, which will help you to reduce the value of the number of exceptional edges, if it is possible. Okay. I try to define some type of interchanging of vertices between the two components so that this interchange brings down the number of exceptional edges. I have defined two such methods of bringing down the exceptional edges. Okay, fine. So my algorithm is this. This is the final algorithm using DFS for a cellular manufacturing problem. So input is a connected bipartite graph. Output is a two-cell partition. And number R, which is the number of exceptional edges in your solution. Okay. So this is my algorithm. Here I am doing the interchanging business to see whether I can bring down the value of beta still further. If not, you can stop even here, it's not a problem. Okay. Fine. So this is the algorithm that we have developed for solving the cellular manufacturing problem of splitting into two cells. Can you extend it for 3 cells or 4 cells? That is not difficult. See, instead of removing one edge from this tree, remove 2 edges. That's it. Suppose I remove P7, M7 and P1, M1. I remove 2 edges. Then I get 3 cells. Okay. So extending this for more number of cells is not a difficult problem. Okay. Fine. Having developed an algorithm for solving a practical problem, the reviewer will ask, what is the complexity of the problem? How difficult it is to implement the algorithm? What is the complexity of the algorithm? Okay. So what is the complexity of the algorithm? What is the complexity of DFS? Every time you are traveling an edge and visit an unvisited neighbor until all the vertices are visited. So what's the maximum travel you may have to take? Suppose the graph has 100 edges. How many visits you have to do? You start from a vertex, visit, keep on visiting, backtrack, keep on visiting, and so on. So it won't go beyond the number of edges in the graph. The complexity will not go beyond the number of edges in the graph. And for this interchange, it is simply linear. Therefore, my algorithm, the complexity is order of m, where m is the number of edges and m is order of n square, because maximum number of edges in the graph on n vertices is n choose 2. It's order of n square. So you see, the complexity of my algorithm is order of n square. It is a polynomial type algorithm. Okay. So efficiency is fine. How good is algorithm? How good is algorithm? Okay. How good is algorithm? For that purpose, I did a very peculiar exercise. What exercise? I'll tell you. Comparison of my algorithm with other algorithms. I took 20 problems from the existing literature. 20 problems from the existing literature, where you have number of machines, number of parts, and the source of the paper where this problem has been studied. And they have given a solution for the cellular manufacturing problem. So it shows 20 problems from the already published paper and collected the solution as presented in the original paper. Okay. Then for all these problems, I applied my DFS algorithm and got the answer. And I compared. For all the 20 problems, I did this exercise. Okay. This is to make the graph, make the paper stronger. Okay. To make the paper stronger. So these 20 results are given in this table. 20 problems, the size of the graph, number of exceptional elements, and the other measures of efficiency. This is for the known algorithm as given in the original paper. And this is the algorithm that I have developed. And I got the answer from my algorithm. Okay. So you see here, for the first problem, for example, cell size is 7 plus 4 and acceptable edges is 2. And for the known algorithm also, it is 7 plus 4 and 2. So my algorithm is not bad. It's as good as the other algorithm. Okay. So I found that for the first 13 examples, my solution coincides with the known solution. You compare the E row here and the E row here. Compare. You will see that they're exactly the same. So my algorithm doesn't give a bad answer. It is already it's giving at least as good as the known algorithm. As good as the known algorithm. Okay. And for 4 cases, my solution gives a better solution. My algorithm gives a better solution. For example, for problem number 15, my algorithm gives 12 exceptional edges and 7 plus 11 size. The original paper algorithm also gives 7 plus 11, but their exceptional edges is 14. So my algorithm gives a better answer than the existing algorithm. Again, it happens for example 16. It is cell size is 13 plus 20, exceptional edge is 8. For me, cell size is 14 plus 19, a small adjustment, but exceptional edges come down from 8 to 5. Okay, exceptional edges come down from 8 to 5. Again, for the last example, the cell size in the original paper is 22 plus 20. My algorithm also gives 22 plus 20. My algorithm gives 7 exceptional edges, 16 exceptional edges, whereas the original algorithm gives 21 exceptional edges. So these 20 examples, which I have randomly chosen from the existing literature, shows that our algorithm is as good as the existing algorithm and sometimes better than the existing algorithm. Okay? As good as the existing algorithm. I am not getting a bad answer, which is bad than the existing answer. So my answer is as good as the existing answer or better than the existing answer. So this justified that our algorithm is really efficient. And that is why the paper got accepted without any problem in a mechanical engineering journal. Okay. So this is how we solved this cellular manufacturing problem using depth first search. Okay, good. Now, why should we study this problem? It is good for the industry to go for cellular manufacturing system. In the existing system, the parts will travel in a sequential manner and will taken to different machines. It may backtrack. Whereas if you had a cellular system, within the cell, lot of work has been completed. Only for exceptional cases, you have to move the part to another cell. So monitoring the manufacturing process is much easier. At the cellular level, you can monitor the manufacturing process. Secondly, when cellular system is formed, the workers in a particular cell became a master of that process because they don't do anything except working within their cell. So work efficiency is much better if you follow the cellular manufacturing. Okay. I will tell you the major advantages. Many firms utilizing cellular manufacturing have reported that there's an immediate improvement in performance and only relatively minor disadvantages. So it's the immediate improvement in performance. Okay. And further, there is include in reduction in work in process. Finished goods are given. Lead time comes within the time. Okay. Scrap is minimized. Direct labor is easier. Workspace is minimized. So these are the some of the advantages in following the cellular manufacturing system. I'll give a concrete example. Quality control is much enhanced because quality can be controlled at the cell level itself. Okay, at the cell level itself, the quality can be easily monitored. So quality control becomes much easier. Good. Then when there is a problem, the root cause for the problem can be easily identified because you can precisely pinpoint the problem comes from the particular cell and proceed to rectify the problem. Okay, so root of the problems can be easily identified and rectified because the cell is small when compared to the full manufacturing system. So a study in US was taken, a survey of 53 US companies introducing cellular manufacturing system have met with success. And they have reported that reduction through input time is 45.6%. Reduction of work in process is 41.4%. Reduction in material handling is 39.3%. Reduction for setup time is 32.3%. Improvement in quality is 29.3%. So all these surveyed companies supported the cellular manufacturing concept, saying that it is extremely benefit and much more than the cost involved. This is reported in this particular paper published in 2002. Okay. Okay, one more interesting example. Standard, there's one company called which Triban Bearing Company, who are manufacturing carbon composite parts and shapes. See, with using carbons, they produce different parts and shapes. They had a lot of problems in the family. The product flow was highly erratic. Work in process was very high. The quality is very poor. There is no accountability in the system. And as a part, so many of the customers started leaving and going to another company. So they were in a very big problem. So they were not able to manage the company. They decided to sell the company right away. So Triban Bearing Company, faced with terrific loss in the business and could not manage to run the manufacturing factory, and they sold the factory straight away to another company called DuPont. So DuPont purchased this company and they decided to implement cellular manufacturing right away. And within 2 years, the plant, they installed 6 work cells and cost of productivity improved by 100%, delivery within time increased by 75%, and a company which was almost at the point of getting closed became a tremendous profit-making system after the implementation of the cellular manufacturing problem. Okay. So before switching over to cellular manufacturing, they had a total annual revenue of $10.6 million and 106 employees were there. After the implementation of the cell in 1998, within 3 years, the revenue became from 10.6 million to 31 million. Okay. And 11 work cells, the number of employees slightly increased, but it was not a problem. Okay. Because the profit is so much that they are not worried about increasing the number of employees. So this is a success story of implementation of group technology and cellular manufacturing system in a carbon producing company. Good. So benefits have been well documented, and there are some limitations. People say flexibility in the manufacturing process is coming down. Flexibility is coming down because I have to work within the cell. Then when there's a need, I have to move to another cell. Not much of flexibility. Okay. That is one disadvantage expressed by a set of people. And then when a new development takes place in the industry, new machines are to be added. Okay, new parts are to be produced. So then you have to reorganize the whole cellular problem. And sometimes that may be very, very expensive. So that is one limitation pointed out by experts. When you go for upgradation of the system, cellular manufacturing system may be more difficult to implement upgradation in the system. So these are some of the limitations reported in the literature. Okay. But anyhow, the benefits are very high, and it's a very nice mathematics problem applicable in manufacturing industry with excellent graph theoretic parameters to be studied. So this is roughly what I wanted to talk about today. Now we are ready for questions. A lot of Indians have contributed to this problem as you look at the references. Okay. So questions are welcome.
Thank you very much, sir, for this wonderful talk.
Thank you.
I'm trying to find out question in the chat box YouTube link.
Sir, I want to ask one question.
Okay.
Sir, is there any application of graph theory in approximation theory also?
Graph theory in which area?
Approximation theory. In approximation theory, sir.
See, so many optimization problems involve graph theory. So many optimization problems. Okay. So many graph problems can be converted to an integer programming problem. Okay, so many graph theoretic problems can be converted to an integer programming problem. So many optimization problems are available within graph theory.
Okay, sir.
Excellent applications.
Sir, how this application is related to operator theory? I want to ask you that.
See, you have to first choose your appropriate problem.
Okay, sir.
And then go for a modeling. As done here. First, the problem is cellular manufacturing problem. Then mathematical model comes. Don't start with the model and search for a problem that can be solved using that model. That's not good. Okay.
Okay, sir.
Start with a good problem, good optimization problem, and try to see how that problem can be reformulated using some mathematical terminology. It may be graph theory, it may be OR, it may be any other branch of mathematics. Okay. Good.
Sir, can you suggest any paper related to this application in operator theory? Can you suggest any paper in which we can see the application of graph theory, approximation analysis, or operator theory?
Traveling salesman problem is 100% a graph theory problem. Very difficult problem. It's a difficult problem. Finding a Hamilton cycle. It's a very difficult and unsolved problem. Okay. Transportation problem. It can be formulated in terms of graph theory.
Okay, sir.
Yeah. So many problems you can.
Sir, I want to ask one thing. How much biology do we need to know to work on this kind of problem, sir?
For this problem.
Yes, sir. How much biology we need to know? Like I had some exposure to biology, but if I want to start
This
work
problem
on
doesn't involve any biology. This
sir?
problem.
Okay, this problem does not need much biology, sir.
No biology is required.
Okay.
Why biology comes here?
No,
It's
I was
only splitting the graph into components. That's all.
okay.
So if you
So we don't use any property of cell or all those
this cell
things.
is not the cell of biology.
Okay.
Okay. Don't confuse with the cell in biology. Here cell is a self-contained subsystem of the
Okay.
big manufacturing factory. Okay. It's a
Okay.
well-defined subsystem in a
Yes, sir.
large system. So the word cell perhaps gives a confusion.
Okay.
Yeah.
Any more questions from anyone? So let's again thank Professor S. Arumugam sir for giving these two wonderful talks in our 2-week refresher course on applicable mathematics. Thank you, sir.
Thank you so much, sir, for explaining us in detail about cellular manufacturing system.
And also for being an inspiration to all of us that during such pandemic times, you're so enthusiastic, positive, updated in research.
Okay, so thank you very much for the opportunity.
Thank you, sir.
Thank you, sir.
Okay. So I'm ending this meeting now.
Okay.
Okay. Bye, everybody.